Dear students, in this video we'll be discussing the string matching algorithms. String matching algorithms are very important in computer science. They have applications in compiler building, in dictionaries, in search engines, in bioinformatics, and many more applications. We'll be discussing different string matching algorithms and also study the time complexity of those algorithms and see their applicability also. The different string matching algorithms which we are going to discuss in this subject are the naive string matching algorithm or the naive string matcher, the Robin-Karp algorithm, the finite automaton, the Knuth-Morris-Pratt algorithm, and the Bayer-Moore algorithm. In this video, I will be discussing in detail the naive string matcher and the Robin-Karp algorithm. Before we take up the string matching algorithms as such, some terminology which we will be using in discussing the algorithms is important. So what I'll do is I'll try to introduce to you the terminology which we are going to use. Basically for string matching, we need two strings to be matched. Here we define or we describe one of the strings as the text, and it is represented as t, and t from 1 to n of length n, and there is a pattern p which we want to match whether that pattern exists in the text, and it is of length m, p 1 to m, and m is generally less than n. We also assume that the elements of p and t are characters drawn from a finite alphabet sigma, and it can be just numbers, it can be English alphabets or whatever. We say that the pattern P occurs with the shift S in the text if the pattern and the text match as shown in the figure. Here the shift is 3, and after a shift of 3 there is a match of the pattern in the text. We continue with the terminologies and the notations. We denote sigma star, or we use sigma star to denote the set of all finite length strings formed using the characters from the alphabet. For example, if the alphabet is all numbers 0 to 9, 21 is part of sigma star, 391 is part of sigma star, and so on. The zero length empty string epsilon also belongs to sigma star. The length of the string x is denoted by the absolute value of x. The concatenation of two strings x and y is denoted by xy, and its length is absolute x plus absolute y. It is said that the string w is a prefix of string w denoted by w prefix x if x is wy. Similarly, w is a suffix of a string x denoted by w suffix x if x is equal to yw. And notice this, w is part of x, but it is after some string x, string y, so we say w is a suffix of x. It is at the end of x. Overlapping suffix lemma. Suppose that x, y, z are strings such that x is suffix of z and y is suffix of z, and if x, absolute value of x, is less than or equal to absolute value of y, then x is a suffix of y. If in the other case x is greater than or equal to y, then y is a suffix of x, and if both x and y are having the same value, then x is equal to y. For brevity, the k character prefix p of 1 to k of the pattern p1 to n is denoted by pk. Similarly, tk represents k character prefix of t. Using this notation, we can state that the string matching problem is finding all the shifts s in the range 0 to 0 less than or equal to s less than or equal to n minus m such that p is a suffix of t of s plus m. Yeah, that is, we are talking about finding all locations s. All locations where we have a shift s such that p is a suffix of t of s plus m. That is, after the shift, m characters match or the same as the pattern p. Now, coming to the naive string matcher, it's a very simple algorithm. Basically, what we do is we try to put the pattern below the text, match character by character, and if there is a match, we say there is a match with a particular value or a shift of s, and if not, we go or we shift the pattern to the next character location, and again do the same thing. So it is a simple thing. First in the step, n is the length of the text, m is the length of the pattern p. Now for s is equal to 0 to n minus m, check why only n minus m, because other than if you go to n minus m plus 1, the last character of the pattern will overshoot the text, hence only up to n minus m. So if p is equal to, if p of 1 to m is equal to or is equal to t of s plus 1 to s plus m, then print pattern occurs with shift yes, otherwise go to the next shift. So the time complexity, as you know, it's very simple. The loop in line numbers 3 to 5 runs n minus m plus 1 times, and the conditional match takes m matches, so it is n minus m plus 1 into m. This is the knife string matchup. This is an example. As I was telling, you put the pattern with s is equal to 0, no shift. The first character matches, the second character does not match. So you make a next shift, that is you put the first character of the pattern below the second character of the text. Again there is no match, shift next, s is equal to 2. There is a match of all the three characters where A, B is the pattern. Print it out and again shift to the next location. There again the second character does not match. The algorithm will end here. Notice the length of the text here is 6 and the length of the pattern is 3, and we can see n minus m is 3 only. So we are going to, after 3 shifts, we are going to stop at this point. This is the knife string matcher algorithm, and it is easy to see what is the time complexity. This will, for very long string matches, this is going to take a lot of time, hence researchers have worked to produce much efficient algorithms. One of such efficient algorithm is the Karp algorithm. This algorithm makes use of the elementary number theoretic notions such as equivalence of two numbers modulo a third number. Basically, this algorithm uses theta of m pre-processing time, and in the worst case running time of theta of n minus m plus 1 into m, which is similar to the knife string matcher, but on certain assumptions average case running time can be brought down from this value, which will be much better. So for understanding this algorithm, we'll assume it can work for others also. We'll assume that the alphabet is made up of 0 to 9, that is all the numbers, all the numerals from 0 to 9, and each character is a digit in radix d notation, where d is the absolute value of sigma, which is nothing but 10. Hence we can view a string of k consecutive characters as a length k decimal number. Given a pattern p1 to m, let p denote its corresponding decimal value. Similarly, ts represents the decimal value of the length m substring t of s plus 1 to s plus m for s is equal to 0 to n minus m. Now s is a valid shift if and only if ts is equal to p. If one can compute p in theta of m time and all ts values in theta of n minus m plus 1 time, then we could all determine all valid shifts in theta of m plus theta of n minus m plus 1, that is equal to theta of n time, by comparing p with ts values only. We can easily compute the p value of p in theta of m time using the Horner's method, which is given over here. P is equal to p of m plus 10 times p of m minus 1 plus 10 times p of m minus 2, and so on. Similarly, we can compute t naught from t of 1 to m in theta of m time. The remaining n minus m values can be computed in a constant time using the method outlined here, and the total computation time of all theta values will be theta of n only. How do we compute that? T of s plus 1. From t of s we can compute t of s plus 1 as 10 times t of s minus 10 to the power of m minus 1 t of s plus 1 plus t of s plus m plus 1. Notice this, we are subtracting 10 to the power of m minus 1 into t of s plus 1 because the most significant digit is left out, and we add one more digit to the right, that is the least significant digit, and that is going to be simulated by this particular computation. And similarly, for ease of computation, we work in modulo arithmetic as p and t values may be very large. So before comparing p and t values, we compute their equivalent modulo q. So if we employ a DRE alphabet, then we can choose q such that dq fits within the computer word. It should be WORD, not WRLD, the computer word. And in such a way, the matching will take place in a very small time, a very small constant time. Hence the computation of t values can now be modified as per the formula given below. T of s plus 1 is d times t of s minus t of s plus 1 into h plus t of s plus m plus 1, the whole in mod q, where h is d to the power of m minus 1 mod q. For our values, for decimal alphabets, it is d will be 10. This solution of working in modulo arithmetic is not very perfect, as it may produce valid match or spurious sets. Hence, additional check is performed on a value of p and t match. We'll see what are the spurious sets now. If you take this, let us assume that 31415 is the pattern. If you do it mod 13, you will get a value of 7. So in the text which is given over here, certain values are computed, and you can see here for the second highlighted part of the text, the value is 7, and for the pattern also it is 7. But if you see the values over there, they do not match. So this we can refer to as a spurious set. So we do computation as outlined previously, and also once there is a same value, we do a character by character match, and that is how the Robin-Karp algorithm works. We'll see the Robin-Karp algorithm now. So in the Robin-Karp algorithm, first we find the length of the text, then the length of the pattern in m, then we compute h as we already defined as d to the power of m minus 1 mod q. Then we start with the value of p and ts. Initially we compute for s is equal to 0, that is why we call it as t naught. For I is equal to 1 to m, p is equal to dp plus p of I mod q. This continues and we get mod q value for the m characters. Next we go on matching. For s is equal to 0 to n minus 1, if p is equal to t of s, then we again do a comparison. P of 1 to m is equal to t of s plus 1 to s plus 1. Print the pattern occurs with shift s. If s is less than n minus 1, n minus m, we do recompute t of s plus 1 as we already outlined, and once we do that, we go back. This completes the algorithm. So if you see here, in the worst case, this algorithm is also going to be theta of n minus m plus 1 into m, because there is a n minus m plus 1 loop and there is a m comparison. But if you see this, if p equal to ts, this is going to reduce the thing and you are going to get a lesser time taken by this Robin-Karp algorithm. So the Robin-Karp algorithm takes theta of m pre-processing time and theta of n minus m plus 1 into m matching time in the worst case. The worst case time complexity assumes that all shifts are valid, but generally it will not be the case. Probably only C of them may be valid shifts. Hence the time complexity will be big O of n minus m plus 1 plus Cm, that is big O of n plus m. For this time complexity to be true, the expected number of valid shifts should be very small. That is big O of 1, and the value of q chosen should be larger than the length of the pattern. For as further as m is far less than n, the time complexity will be big O of n only. So that is the Robin-Karp algorithm. We have now discussed two algorithms for string matching. One is the naive string matcher, the second one is the Robin-Karp algorithm. There are other algorithms, which is a finite automata algorithm, which we'll discuss in the next video. Thank you, students.